Hi guys, hi everyone, good evening to you all. Am I audible and visible to you all? You can just write a yes in the chat box if you can hear and see me. Just write a yes in the chat box if you... Okay, great. That means we can start. Today's question was a super easy question, to be very honest. So honestly speaking, the discussion is going to be a breezer because it's a very conventional question, and this is one of those questions which I call as interview cliche question because it's very frequently asked in interviews to check some basic coding skills of the candidate. So yeah, I would want to know that how many of you attempted this question on your own and were able to code it. Rishav is talking about something called as B search. Okay. Rachit was able to do it on his own. That's great. Awesome. Anyone else? Okay. I would recommend you guys to read it because it's a very simple problem statement. As you can read, we have been given an array of integers. The name of the array is nums. The important thing is that this array is sorted in non-decreasing order. What is the meaning of non-decreasing order? Non-decreasing order means that the elements will never decrease. You may have duplicates, but the elements will never decrease. So you can have 1, 2, 3. So you can see as you are moving, the values are not decreasing. After this, you can have a 3, as I told you, and then you can have a 4, you can have a 9. So this is what is a non-decreasing array, in which the elements are increasing and at times they are fixed. Again, they can be fixed if there are duplicates of 4. Now you have been given a target, and what you have to do is you have to find the starting and ending position of that target. So for example, let's say the target given to you is 3, then I can clearly see that the first index of 3 is this, which is index number 2, and the last index of 3 is this, which is index number 4. So I can say that if my input is 3, the first index is 2, and the second and the last index is 4. So my output should be a pair 2, 4. It can be a pair, but here I have to return a vector. So what I'll do is I'll create a vector of size 2, and inside that I'll put the first and the last index. Further, it also says that if the target is not found in the array, let's say if your target was 5, then there is no first index and no last index. So in that case, you're supposed to return -1 each. As simple as that. Now, it also goes on to say that your algorithm should run in order of log n time. So we'll talk about this log n thing. By the way, whenever you see that there is a question which is demanding logarithmic complexity, log of n, what immediately comes to your mind? Which algorithm rings a bell? If you have read about it, binary search, isn't it? See, binary search, I would say, is the easiest skillful algorithm. There are so many skillful algorithms, like you have got things like topological sorting, you have got Kruskal's algorithm, Prim's algorithm, Dijkstra's algorithm. They are very skillful in nature because they do complicated tasks, but it's not very easy to implement them. But when you talk about binary search, it is very easy to implement binary search. Anyways, a binary search offers a logarithmic complexity. If the search space is of size n, the complexity is log of n, and as a result of that, whenever we see a question demanding log of n complexity, binary search comes to our head. Okay, we'll talk about binary search in some time, but can you tell me the brute force way to solve this question? So the brute force way will be super easy. We all know that because the array is sorted, so our job is super easy. Correct? What we can do is that we can start scanning the array from left, and when I encounter my target at the first place, I can record it, and when I encounter it at last place, I can record it, and that's it. The job will be done. Yeah, this is also something which is called as linear search. Linear search is nothing, it's just like starting from index 0 and then proceeding one by one in the right direction. So what we can do is, I can say that let me create an answer vector. The size of this answer vector can be 2 to start with. And now I'll have two variables with me. I'll call them first and last. So first will store the first index of my target, and last will store the last index of my target. I can initialize both of them to -1 because if you have read the question, it says that if the element is not found, you can return -1 each. So this is how I have initialized them. And now what I can do is that I can simply write a for loop which iterates on this vector. So I equals to 0, I smaller than nums dot size, I plus plus. Now if I find that the current element, which is ith element, is equals to the target, then my eyes should lit up. Why? Because if the current element is equal to target, that means we are touching something which has been asked in the question. If let's say it was 3, which has been asked in the question. Now the important thing is that when do you want to update this element first? You would want to update this element first if and only if you are encountering it for the first time. So what you can do is you can put an if check and you can say that, hey, you know, if I found that first was equals to -1, then I'll go ahead and update the value of first to become equal to the current index, that is I. Okay, apart from this, I'll do one more thing. I'll update my last also to become equal to I. I'll tell you why I'm doing this. I'm doing this because what if there was only one occurrence of 3? If there was only one occurrence of 3, then the same index would have been first and the same index would have been last, which is index number 2, and thereby your output would have been 2, 2. So whenever it happens, I am updating both first and last. What should I do in the else case? Tell me. Else case means that you encountered a 3, but this time your first was not -1. If your first was not -1, it means that you are encountering it for the second, third or fourth time. So in that case, I am just going to update my last. Now it means that by the time this particular loop is over, first and last will denote the index of first and last occurrence of target. Isn't it, guys? Yes or no? Right? So finally all that I have to do is I can simply set answer of 0 to be first and answer of 1 to be last, and then I can return this answer, and then ideally the job should be done. If I submit it, it's accepted. It's accepted, but you can see it's relatively slow. So now we have to think about the order log-n based solution. But before that, I would ask you this question. Is everyone clear with the current code? How many of you have perfectly understood the current code? Okay, awesome. Now, see, a lot of you talked about binary search when you saw order log-n expectation. What is the primary requirement for binary search to work? When does it work? It works when your search space is ordered. See, a lot of people feel that binary search can only be applied on an array which is sorted. But guys, it is not right. And I can give lots of examples to that, but that might not be relevant at this point of time. For example, I'll tell you, let's say I give you a random array, and this array looks like look at this array and tell me, is this array sorted? Is it sorted in some ascending or descending order? The answer is no, it is not sorted. But is there an order that you can see inside this array? Come on, who will tell me the order? Is there some kind of order, some kind of pattern? The answer is yes. The order is that initially you have even, 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 and then you have odd, odd, odd. So I can say that I have even element, then again I have even element, then again I have even element, then again I have even element, and after that I have odd, 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 correct? So whenever you have a pattern like this or any random order, in that case also binary search can be applied. So if somebody gives you such kind of array and asks you that, hey, tell me the first index of odd element, then what is the first index where odd element is coming? It is this index. Can you find that out using binary search? The answer is yes. Okay, how to do that? For that, we will quickly revisit the idea of binary search. So guys, what is the idea of binary search? Is there anyone here who does not know anything about binary search? Please feel free to type no if you do not know anything about binary search. I can give you a quick intro to it if that's the case. So basically, what does binary search do? If you have an array which is ordered, and let's say for now it's ordered in simple ascending order, 2, 10, 12, 15, 16, 67, 90, something like this. And let's say you have been given a target and that target is equals to 90. So if you have to search whether 90 is present inside this array or not, then how do you go about it? One way is that you can do a linear search from beginning till the end. You can run a for loop like this. The time complexity of that will be order of n, correct? But the second way is that what I can do is every time I can attack the middle element. Now why I'm saying attack the middle element, guys, think of it in this manner. Let's say you compare your middle element of the array with the target. Now, if your target is greater than the middle element, can I say that answer will lie in the right portion? Yes. Why? Because if your target is greater than the middle element and if your array is sorted in ascending order, in that case it can never lie behind. Because behind 15 you will only get values which are smaller than 15. So if you found out your target to be greater, that means now your search space is the right half. But on the other hand, let's say your target was 9. And if you would have realized that, hey, your target is smaller than middle value, in this case, would you want to go to the right half? No. Where would you want to go to? You would want to go to the left half. And you would say that, hey, my answer probably lies in the left half. So do you see what is happening over here? What was the initial size of your search space? How many elements were there at your disposal at the beginning? There were n elements, correct? After you compared your target with middle element, your search space was either the right half or it was the left half. Never it was both of them, correct? So then your search space became from n to n by 2. Similarly, let's say now this is your search space. And now again what you can do is you can compare your middle element with this, and based on that you can decide whether this target should lie in the right half or it should lie in the left half. So from n it would become n, from n it has become n by 2, and from n by 2 it will become n by 4. And finally it will become 1, and then finally it will become 0. So can you tell me how many steps are there from here to here? So you have been given a number n, and if you repeatedly divide it by 2, then how many steps will be there? The number of steps will be log of n base 2. That's it. And that is the reason number of comparisons which happens in case of binary search is just log of n base 2. But in case of linear search, it is order of n. Okay, so here, if somebody has to implement binary search, it's very easy to implement. Every time you can maintain two things. You can maintain low, which initially is 0, and high, which initially is n minus 1. So low is pointing to the first index of your search space, and high is pointing to the last index of your search space. And every time you can find out a mid. Your mid will be nothing, it is the middle point, so it will be low plus high, divide 2. Now at this particular index, you can see which element is there, and you can compare that element with your target. And based on that, you will either change your low or you will change your high. Now tell me one thing. To start with, this was your low and that was your high, because this entire array was your search space. Correct? Now, if you realize that your target is, let's say, 22, and 22 is greater than 15, in this case, you would want this portion to be your search space. If you want this portion to be your search space, which variable will you change? Will you want to change your high? The answer is no, because high is already pointing to n minus 1. So what would you want to change? You would want to change your low. And how should you change it? Your low should become equals to mid plus 1, because if this index is mid, and if you change your low as mid plus 1, that means now this is going to be your next search space. But on the other hand, what if your target was, let's say, 11? If your target was 11, you would want to consider this search space. If you want to consider this search space, would you change your low? No. You'd just change your high, and what would your high be? Your high would be nothing but mid minus 1. That's it. So this way you can keep changing your low and high accordingly. Now eventually, do you know what happens? If the element is not found, eventually the value of low becomes greater than high. Because imagine this is your low and that is your high, and every time your low and high are approaching close to one another, and if the element was not found, what will happen is that low and high will supersede one another. Now the moment they supersede one another, low will become greater than high and the algorithm has to terminate. So this is the basic idea behind implementing binary search. Okay, I think we talked enough about binary search. Now let's talk about the question. This question is not just about checking whether a target is present or not. This question is about explicitly finding out its first index and last index. You understand that, right? So in this case, I have to do little bit of improvisation. So it's just a very simple improvisation of binary search. What I would say is, let me remove this piece of code for now. This also. And now what I'll do is, I'll write a very simple method, int first. What this method will take is this particular vector and this particular target. Okay, and now what it will do is, it will tell me the index where target appears for the first time in this vector. And for that, I am going to use the idea of binary search that I just spoke about. So what I am going to do is, I am going to initialize a variable called as low, which is 0, and a variable called as high, which will be nums.size minus 1. It's equivalent to saying n minus 1, right? Okay. Now what I'm going to do is, I'm going to say while my low is smaller than equals to high, I'll be writing my logic of binary search. And what is the logic of binary search? You calculate the midpoint, which is nothing but low plus high divided by 2, correct? After calculating this midpoint, what is the next thing that you do? So tell me one thing. If you find out that your current element is greater than the target, if your current element is greater than the target, like let's say this was your mid and let's say your target was 7. In that case, which half do you go to? Do you go to the right half? No, you go to the left half. And if you have to go to the left half, what do you change? Do you change your low or high? You change your high, and your high becomes mid minus 1. So I can say that, hey, if this is the case, then my high should be changed, and it should be changed to mid -1. That's it. Okay. Else if the current element is smaller, let's say it is smaller. In this situation, what would you do? So let's say this was your middle element, and what you wanted to search that was actually greater than this. So let's say you were searching for 92. In that case, where will you go? You would want to go to the right side, correct? Now if you want to go to the right side, which variable will you change? You will change your low. So your low will become m+1. Okay, so this much of code is consistent with whatever we have talked about, right? Okay, how about the else case? What will the else case denote? This if case is for the situation when the middle element is greater. This is for the situation where middle element is smaller. So naturally this will be for the situation where middle element is exactly equal to your target, right? Let me change this array a bit. Here, let's say your target was 15, and you'd have found out that, hey, this middle element is also 15. Would you want to return this index? Would you want to return this index? The answer is no, because this index is neither the first occurrence nor the last occurrence, and moreover, my current function should return the first occurrence. So just because your middle element and the target element are matching, it does not mean that you will return that index. So what to do? In this case, I have to be a bit careful. What I'll do is, I'll simply check that what is the element which is lying just before it. So let's say the element before it was 13. And if I find out that the element just before it is not equals to target, if the element just before it is not equals to target, then I can say with surety that this is the first occurrence. Can I say that? Use your common senses. The answer is yes, because the array is sorted. And if the element before it is not equal to that, that means this itself has to be the first occurrence. So if this is the case, I am simply going to return m. That's it. But if that is not the case, then what to do? Let's say this was 15, and let's say this was also 15, and you were here. Now you found out that your previous element is also equals to the target. So now this would denote a situation where you can confidently say that your answer is lying in the left half. If your answer is lying in the left half, which variable do you change? You change your high. So in the other case, what you are going to do is, you're simply going to change your high to mid -1. Now there is one very important case to take care of over here. And what is that case? See, whenever you are writing indexes like these, m-1, m-2, you have to be careful about index out of bound exception. Because if at any point of time your m is 0, then 0 minus 1 will be -1. So I'll give you a situation. What if you had a 15 here also? And what if, let's say your mid was here? If your mid was here at index 0, would you want to check 0 minus 1? No. And it does not make sense, because if you are at index 0, and if that is equal to target, then it is guaranteed that that itself is the index of first occurrence. As simple as that. So I can handle that boundary condition by writing this code that, hey, if I find out that my m is equals to 0, I'll simply go ahead and return m. That's it. Okay. Now this is our complete code. Now understand one thing with a pinch of salt, that hey, at times it can happen that the target was not present only. What if your target was, let's say, 19 or 99 or something like that? If the target was not present, this loop would be over without returning any value. So in that case, finally, I would want to return a value of -1 from here. That's it. So this is our simple code which returns the first occurrence of this target from this vector. And because we have used binary search, where we are making our search space half each time, so the number of iterations will be log n. So the time complexity of this is log n. However, this algorithm is only finding the first occurrence. Now, can you write an algorithm to find the last occurrence? How many of you can do that? Okay, one of you is asking, will it be wrong if I use binary search 2 times, one for start position and one for end position? No, why would it be wrong? That is exactly what we are going to do. 2 into log n is log n only, asymptotically. There is nothing wrong with that. That approach is totally good. Okay, cool. So let's say now we want to find the last occurrence. See, if you want to find the last occurrence, what part of code is going to change? By the way, what is the last occurrence of say 15? This index. And what is this index? 0, 1, 2, 3, 4, 4. See, can I say that this condition and this condition, basically both of these conditions will continue to remain however they are? I mean, in this code, they will continue to remain however they are. Can I say that? Of course I can say that, because if you want to find out the last occurrence of 15 and let's say your mid is pointing to an element which is greater, then you would want to come left. If you want to come left, you would want to change your high. With the same logic, if let's say you are ever pointing to an element which is smaller, you would want to go right. And if you want to go right, you would want to change your low to m plus 1. But what to do in the else case? Here in the else case, if you want to confirm whether your current index is the index of last occurrence or not, then instead of comparing previous element, you would want to compare next element. And what is your next element? It is at index m plus 1. So if you happen to see that your nums of m plus 1 is not equals to target, like let's say if your m was here and nums of m plus 1 is not equals to target, in that case, could you confidently say that, hey, this itself is the index of last occurrence? The answer is yes. Of course, we could say that, right? So in this case, I'm just going to return m. Otherwise, what to do? So just imagine you had a 15 here also and you had a 15 here also. And this was your midpoint. Now, if you see that the right side element is same as 15, that means you can say it with surety that your answer is in the right half. If your answer is in the right half, which variable will you want to change? Would you want to change high? No, you'd want to change low, and your low would become equal to m plus 1. Now, what is the edge case here? The edge case here is, in this question, you were checking previous element, but in this question, you are checking the next element. Now, whenever your mid is at the last element, there would be no next element. I mean, m plus 1 would give you index out of bound exception. So you can handle that differently. You can say that, hey, if it ever happens that my midpoint is equals to nums dot size minus 1, then it means that index itself is the index of the last occurrence. Sorry, I think I made change at the wrong location. So I've got to change it. This will remain as it is, and this will remain as low equals to mid plus 1. Sorry, this will remain as high equals to mid minus 1. This was right. In this case, the difference will be that here, if m is equals to nums dot size minus 1, then I am going to return m. So this is our simple code for returning the last occurrence. You can see everything is same. These two logics are exactly the same. Here, if we find that the current element is equal, then we compare our next element with the target. If our next element is not same as the target, that means the current index is the answer. Otherwise, we know that our answer is in the right side, so we are changing our low to m plus 1. Now, at times it can happen that our mid is at the last index itself, so in that case we will simply return m. And if it ever happens that the loop has got broken, we will return minus 1. Is it clear? How many of you are clear with the implementation of first method as well as last method? So if it is clear, all that you have to do is you have to call the first method and you have to pass your nums and target to that, and you have to call the last method and you have to pass the first and the nums and target to that. Finally, you can just run your code and then you can try to submit it, and it has been submitted, right? So this particular approach will have a time complexity of log of n, because when we call first, when you call this method first, it is going to work in log of n time. When you call this is also going to run in log of n time. So log n plus log n is 2 times of log n, 2 can be ignored. So overall it is log of n. It is log of n, and log of n in time complexity, and space complexity is order of 1 because we are not using any extra space at all for the purpose of this question. Cool. So that was all about it. The next thing that you guys can do is when you go back from here, you can probably search for similar questions. You know, here you have some of them, and you can try attempting them on your own, and then you can see whether you are able to apply this binary search idea over them or not. By the way, was it clear to everyone that how we could use binary search to find the first and last occurrence? Do the code size matters, like someone writing a short code and someone writing a... Yeah, it depends on the nature of interview. If the nature of interview is to check your clean coding skills, in that case it would matter. Okay, so that is something which you can take as a food for thought. Maybe can I pass a third argument to a function, and based on that third argument can I quickly decide whether I was looking for a first occurrence or last occurrence. Time complexity wise, it is not going to make any difference. Okay, let me tell you that. But it might make a difference from the perspective of how large your code is, because if you really look at the lines of code here and the lines of code here, there are so many things that are common. The only part which is different is this part, when you compare your last with your first. You can refactor it. You can refactor it very easily by writing a separate method or maybe passing a third argument and deciding things based on that. Okay, cool then. So that's it for today. Let's meet again tomorrow. Probably let's hope we get a better question for tomorrow to discuss. Right, and please implement this question if you have never implemented it, because it's a very famous interview question also. Okay, cool. Bye and good night.